Hello everybody and welcome to a tutorial about Freecad CfdOF, tutorial number 3 in English. In this tutorial I will show how to simulate a movement of two plates. One plate stands still, the opposite plate moves with a velocity of 10 meters per second. We will calculate the force generated by the viscosity of the fluid. This simulation is close to the definition of the dynamic viscosity. This means that this simulation is a verification of CFD. This is a simulation model we will build up. We have two plates. One plate is a lower plate. The other plate is the upper plate. Both plates have a width of 1 meter and a length of 1 meter. The distance between these two plates is 0.1 meter, and they are filled with a fluid between. You see also the assumption for the distribution of the velocity. We assume that we have a linear velocity inside the fluid. If this is the case, this will be shown by CFD. We have also to make some calculations. We will calculate the force generated on the upper plate by the viscosity of the fluid. First, we need the kinematic viscosity and the dynamic viscosity. The kinematic viscosity is given with 0.104. If we divide this by the density of the fluid, we get the dynamic viscosity. As a second number, we calculate the Reynolds number. This is given by the length and by the average speed divided by the kinematic viscosity. So we get a Reynolds number of 209. This might be probably a turbulent flow or not. And last, we take a look on the force which is generated. We assume that we have a laminar flow and we have a linear speed distributions. So we get a shear force. This is calculated with a dynamic viscosity and the gradient of the velocity. We will get a shear force of 0.4 Newton per square meter. And since the area of the plate is also 1 square meter, we get a force of 10.4 Newton. And now let's take a look what the simulation gets as a result. Now let's start with Freecad. First, we start with a parked workbench. Our model is like a cube, so we build up a cube. We go to the dimensions. The length is 1 meter, the width is 1 meter, and the height is 0.1 meter. We also change the position. In x-coordinate, we take minus 0.5 meters. In y direction, also minus 0.5 meters. Okay. So now our model is complete. We can go to the CFD workbench. We built a new analysis container. So first we start to define the mesh. As a measure, we will use G-mesh. The base element size will be 25 millimeters. I do not go to write mesh case and run measures because we need something to refine the mesh. So I go to this and I define the refinement. I pick this plate. It's a 6-phase and the relative element size will be 0.25. In the next step, we will define the boundary conditions. So first we pick the wall on the left, and the boundary condition is open. So you must always pay attention to the coordinates. This is a wall which is in the x direction. We also take the opposite side. Okay, now it's finished. The next boundary condition will be the upper plate. And here we say this is a wall, but the subtype is translating. So we can define a speed. We define a speed of 10 meter per second. So always look in which direction this will run. This will run from open to open. This is okay. In this case, we will rename the label. So the new label will be upper plate. Okay. We pick the opposite side. And this will be the boundary wall, subtype no slip. We also rename this boundary conditions. The label will be lower plate. Okay. So now only two constraints are open. So one will be this side. And the other is this side. So here the boundary condition is wall and subtype is no slip. So that's okay. Now let's take a look on the physics model. The physics model is it's a steady state analysis. Flow is single phase, incompressible, and we want to consider viscosity. The first simulation will be a turbulent simulation using the Reynolds averaged simulation. Okay. Fluid properties. Fluid properties will be, we define this as an oil. We use the oil because of the high dynamic viscosity. As a start condition, in this case, we must specify values. So we say that the initial velocity will be 8 meter per second and the initial pressure will be 0.01 Pascal. So now we go to the mesh. We write the mesh case and then run the measure. This takes some time. So see you later in some seconds. So now the measure has finished. We can review the mesh by clicking on Load Surface Mesh. Okay. Now we see the mesh. We can see that we have the refinement we wanted on the one side. On the other side, we have the mesh is a bit wider, and that's okay. We can close this. And now we can go to the solver. We make a double click on it, and we write the case. So there's only one thing left to do. We want to know the force in x direction, and for this we must edit the one file. This file is called the control dict file, and we must edit a command. The command can be found in a tutorial by Mr. Oxtoby. In this case, I just make copy and paste. I go to and I insert the, so now there are only some things that we have to change. The first thing is the patches here is called wall, but we will say upper plate. And the density, this is a density of 1.2. This is the density of air. So we change this to 780. This is the density of the oil. We can close, go back to Freecad, and let the solver run. Now the simulation has finished successfully. We can review the results with Paraview. We click on Paraview and wait until it started. So we go to the last simulation step. And first we take a look on the velocity distribution in x direction. You see that the highest velocity is only achieved in the highest layer. We can take a look on the velocity distribution over the z coordinate. So plot over line. The point we choose is the point 0, 0. And here also the second point is 0, 0. You can see here the line. And so let's see the values over the z coordinate. Okay, here are many values that are out of interest. We will click them away. The k, the nu, the omega. So we only have the pressure and the velocity. So we want to know the velocity in the different directions. You see that the main velocity is only achieved in x direction. We don't have a linear distribution that we assumed. So, but what we see is that we have a steep gradient towards. And the boundary condition on the left side was 0, that's fulfilled. On the right side we have 10, that's also fulfilled. Now we go back to Freecad and we click on Edit and take a look on the file. You see here a new directory that's post-processing. We go into it, and this is a force. So here you see the force out of the total force in x direction, y direction, z direction. This is the force out of the pressure, and this is the force out of viscosity. It's given for each time step or for each iteration step. So we go to the last step. And here we have a viscosity force of minus 2.7 power plus 0.2. You see that this value is higher than the analytical value. That's of course something that we expected. Now we want to let the same simulation run with a different physics model. So we double click physics model, go into the menu, and we change the model for the turbulence. We change from RANS to laminar, and we say OK. Now we can go to the solver. I've tested this before, and convergence will not be achieved fully. So I say this will stop with 0.002, a little bit earlier. And so now the parameters for the solvers are complete. I can go to the CFD solver, make a double click, write the case. And now I must edit this again, go to System, Contradict, because I want to know the forces. I make here a copy, go back to the editor, insert it, and change the patch from wall to upper plate, and change the density from 1.2 up to 870. And save this and close. Go back to Freecad and let the simulation run. So now the simulation has finished and we will review the results. We start Paraview. We go to the last time step and take a look on the results. Take a look on the speed in x direction. So this looks quite similar to the model with turbulence. We also take a look on the speed distribution. Go plot over line. And the point where we want to plot over, we added the coordinates 0, 0, 0, 0. Okay, apply. And here we see the pressure and the speed distribution. We want to know the speed in x direction. Here it is. You see that the speed in x direction is quite the same as it was for the turbulence model. So again, we take a look on the post-processing directory. Take a look on the forces. So now we see that the forces are comparable to the other results. Now we compare the results. On the left side, you see the analytical approach. You see that we had a linear distribution over the z coordinate. This would lead to a force in x direction of 10.4 Newton. In the middle and on the right side, you see the solutions from CFD-OF, the model that regards turbulence, the model with RANS. This leads to a force in x direction of 271.2 Newton. And a model with a laminar flow leads to a force of 302.3 Newton. You see that the velocity over the z coordinate is comparable, but with small differences. This difference leads also to the different forces in x direction. Conclusions. The CFD solution is different to the analytical model. The speed distribution over the z coordinate is different. This leads to higher viscous forces. And the most important thing is that we've learned something about the boundary condition. A translation can also be a boundary condition. Thank you very much for your attention. Bye bye. Hope to see you in the next tutorial.